So then shouldn't it be A because the EMFs have to be of like
Oh, okay, huh. So in this case, it is correct A, but let us get to the basics. I mean, to the root of why it is changing. Back to the basics. Okay, so Ahan, let's say if this entire coil is at the extreme left. So tell me, Ahan, the flux passing through the coil at the left,
Zero, because
it
nothing's.
is zero, right? Now, once the rod makes an entry, let's say some bit of it has entered. So initially the flux was zero, but all of a sudden the coil feels an X, all these X's, which the coil does not want. So to counter that, the coil is going to produce dots. Is it making sense?
Lenz's law?
Yes. So to counter the cross, the coil is producing dots. Anishka, Christine,
yeah, sir, makes
are you
sense.
able to recall? This we did in class. So dot, now use the right hand rule. So the thumb should be going in the direction of dot and then curl your fingers. So the curling goes like this in an anti-clockwise direction.
Oh, no, I remember it now. You had given us the example of the bar magnet and you're moving it close and then moving it
Yes,
away.
yes.
Yeah, okay.
When exiting, so Christine, repeat the process for when the magnet is exiting. Oh wait,
So when
before the exit, hang on, Christine, before the exit, tell me over here, what will be the induced EMF in this case?
there would be no induced
EMF.
so yeah, because
Why is
it's
that?
constant. Because the
Yes,
area is completely covered and the speed is also constant in this case.
correct. So flux is a constant. At the exit,
Yes.
what will be the direction of current?
So it should be, I think so. Again, you will have it going into the page, so it should be
Yes, so the coil is
clockwise.
producing, correct. So the coil is going to produce X magnetic field, which is clockwise. So now observe entry and exit, the direction of current is opposite. Check. Is it making sense?
Yeah, I
Now
get
we
it.
use the same logic for our question. Here, in this particular question, if the area is reducing, what will be the direction of current in the entire coil?
So, but when we're talking about area, even in the question before, you were considering the area of the square, right? So
Area
should we
of the
be,
coil. Yes.
so should over here we're considering the area of the rod.
No, no, no. It's always the coil. Coil as in it should be a wire all connected. So hang on, let me have a look. In this particular diagram, when I say coil, let me label some points. A, B, C, D, L. All right. So A, B, C, D, L, P, Q, N, S, A. This entire thing is your coil.
Okay,
But in the formula for flux, A stands for the area of the coil inside the magnetic field.
right.
That's why I have shaded this,
Okay,
right? So now this particular area is reducing.
So
So
current is clockwise.
yes, current is clockwise. So if the area is reducing, so Christine, tell me okay, if the entire area is reducing, what will be the direction of induced magnetic field?
Should it be into?
It is into. Because if the area is reducing, the crosses are reducing. So to counter that, rod is going to produce its own cross. And then we use the right hand rule to go clockwise. So the current is actually going down. This was actually tricky. So Anishka and Ahan, check. Is it clear?
Yeah, sir, got it.
Okay, sir.
Very, very good question. So great. All right, one more question we'll do on equivalent capacitance. The next question.
Sir, is it B?
I
4 by
got B
5.
as well. So.
Okay. 4 by 5 C. So, okay. Ahan, explain.
Sir, so the ones in the triangle are parallel together, so you add them up, you get
Which
4.
ones? Hang on. Wait. Let me label the capacitors. Then explain. PQRS.
So P would be parallel to R and Q would be parallel to S, correct?
So P is parallel to Q and R is parallel to S. Yes, correct. And then,
Using that, we get the total capacitance to be 4C,
okay,
and then that's in series with the
this
capacitor
one.
above.
Okay, fine. That is correct. Option B. Anushka, check if you're getting this.
Yeah, sir, got it.
Great. Next. This one was easy. Try this. Okay, these are the options.
So just to confirm, since C1 and C2 are parallel, the
Mhm.
potential difference across them would be the same, right?
Yes, correct.
So is it A?
It is A. Brilliant. How did you do it?
So I don't know if my assumption is correct, but I assume that C3 should equal to C1 plus C2. So
No, 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 no. We can't do that. C1, C2, C3 could be anything randomly.
no, 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 I'm saying that C1 plus C2 should equal to C3, right? Because of conservation of.
C1 plus C2 is equal to C3. No, I think what you mean
No,
is
not the charge, sir.
yes.
Not the capacitance, the charge.
So charge on C3 is equal to
See the charge on C1 and C2.
any, okay, that is actually correct, but can you explain? Wait, let me write down the equation first. What's the logic at work here?